start. I wanted to start today with a few practice problems. So let's do that. Let's do a little try this. So let's take a few minutes and give me the products on these. Okay. So let's take a couple minutes. Look at your starting material, look at your reagents. A couple of these are from a lecture on Wednesday. The other ones are from substitution elimination with alkyl halides. Okay, let's go ahead and take a look at the first one. Remember, whenever you're trying to evaluate what's going on here, you can look at your reagent. And if we look at our reagent here, this is negative, right? That is positive. This is the acetate. Acetate is a good nucleophile. Right. When we look over here at our substrate, we've got a secondary substrate. We've got a great leaving group. Okay. So if we think about what's going to happen here, I've got a secondary substrate with a really good nucleophile. This would fall into the SN2 process. And so with the SN2, I would expect this to do a substitution. And that substitution, I would expect it to be inverted, right? So this is saying SN2, right? This is SN2E2, great leaving group. My best answer here, especially with the acetate, would be SN2 only, or majority, okay? Any questions about that one?
Yes, I have a quick question.
Mm-hmm.
Wouldn't you also get the retention?
Not in an SN2, right? So in
Okay.
an SN2 process, right, you only get inversion. And so
Okay.
with this being secondary with a good nucleophile, I would expect this only to favor SN2 reaction. If the nucleophile was weaker and not such a good nucleophile, then on a secondary, potentially I could have had SN2 and SN1. In that case, I would see some retention as well. But in this case, with a really good nucleophile, I would go SN2.
Okay, thank you.
And SN2 is only inverted, right? Okay, let's look at the next one. Good question. Let's look at the next one. Next one, we've got a T-butoxide. T-butoxide is a big bulky base, right? Or a sterically hindered base. Okay, we have a sterically hindered base. We have a secondary position here, right? Good leaving group. With a bulky base, right? What that does is this slows down SN2, so therefore it favors E2, right? So therefore, with the big bulky base, substitution gets decreased, E2 gets enhanced, so therefore I would expect an elimination here, E2, And you've got two groups of beta hydrogens, but both sets of beta hydrogens give me one product. Okay, so I'm gonna okay, questions about the elimination. All right, the next one is from Wednesday. Here we have an alkene. We're going to have an addition of an alkene. Okay, this reagent here is hydroboration, oxidation. Okay, and the few things we need to know about hydroboration oxidation: one, it's anti-Markovnikov. Okay, and Markovnikov is the most stable carbocation. So this is going to be the anti-Markovnikov. So I'm going to add to the opposite side. And then this is also syn. Syn means that I'm adding both of the groups that I'm adding to the same side. So in this one, if we look at our two positions, which of the two positions are more substituted, the top or the bottom? Well, the top is more substituted. That would be my Markovnikov position. So therefore, since this is hydroboration oxidation is anti-Markovnikov, I'm going to add my OH to the bottom, and I'm going to go ahead and put that in wedge. And then that means my hydrogen on the other position is on the same side. And in this case, I would have the enantiomer. Right, so I'd have that, plus I'd have both of them being on the opposite side. Okay. Questions about syn addition or anti-Markovnikov from Wednesday? And we'll talk about the same concepts as we continue through this chapter. So we'll keep going back to these. The last one, here we have, this one I'll be able to work through the mechanisms with you. We have the nucleophile attacking the electrophile. Right, that gives me addition to give me the more stable carbocation. Right, so I want the secondary carbocation over the primary. And then once I get that first addition, the first nucleophile, electrophile, right, leaving group leaving, then the bromide can come back and attack. And I get the Markovnikov. Okay, so I get the Markovnikov addition to the bromide. Do I have any stereo control here? Well, no, because this one is planar, right? So therefore it could attack either the top or the bottom, and then the carbocation is planar. Right, so whenever we have carbocations, we lose the possibility of stereo selectivity. In the case of the hydroboration oxidation that we had up here, it's not going through a carbocation, and that's why we can end up with the syn addition. Okay. All right, I'll post some homework. I'll post a quick quiz, about 5 questions later today. I'll leave that open all weekend and probably through beginning of day on Monday. It's really for your practice. It'll probably say it's graded in assignment. It's really for your practice. I'll try and have the grades at 0. When I tried to set it up late last night, I was having trouble figuring out how to do that because I haven't set up a quiz for no grade. But I'll try and do it with no grade so you won't get confused on that. Okay, exam is next Friday. Okay, so this is the week if you haven't been studying throughout to get started studying. That exam will be during class time. I'll probably open it 5 minutes early and allow 5 minutes extra. Once you start the exam, you will only have 1 hour, but I'm going to go ahead and open it up a little bit so that you'll have a little bit more time flex around there in case you have trouble getting in to the system. But there's no respondus. It is a quiz bank. So that means that you might not get the same questions as anybody else. In fact, usually the chances of getting exactly the same exam as anybody else will be different. But just like today, if there was a question over SN2, there'll be a question with SN2. You just have multiple versions of that. So doing the quiz will help you see what I'm talking about. All right, so let's continue in chapter 8. We should finish chapter 8 by Monday. Wednesday will be review. What we'll do is do some potential questions, but Wednesday we should be reviewing for the test. We should finish chapter 8 on Monday. So let's continue with where we are. So catalytic hydrogenation is the next section. And here we have the catalyst. And we have several hydrogenation catalysts. So you can have palladium, platinum, nickel works. Often the palladium is on carbon, so you'll see something like this. So what they do is they coat carbon with it. There's platinum oxide, sometimes you'll see that as well. But you'll notice that the main component you're watching for are these three metals, right? So these three metals are the ones that will get you to the product, at least in this. Now this one is heterogeneous. Right, so that means that we have a liquid and the catalyst is solid. Okay, so you're really putting metal into the solution. Yeah, the couple of questions on chat. The exam will be through chapter 8, so we should finish up chapter 8 on Monday, and then that's as far as it'll go. Iron catalyst works, can work. It's not one of the standard ones, and usually you have to have something else in there, such as an acid. So if you look at iron catalyst, it's not quite this straightforward. We'll see in a minute there is rhodium catalysts, but those are not heterogeneous. Those are dissolving metal catalysts. So those are actually homogeneous. We'll look at that. That's later in the chapter. So you will see iron, but if you look, sometimes the iron has acetic acid, or it'll have a protic solvent base in it. Most often, the solvent for this is just an alcohol, right? It tends to be the solvent for choice. So you usually see hydrogen, platinum, and ethanol. Okay, so the way this works is that, and what I'm showing here is the metal surface, right? So this is heterogeneous. The hydrogen atoms, right, are absorbed to the surface of that, and then what happens is the double bond then becomes absorbed. So platinum, palladium, and nickel, mostly platinum and palladium, are known for absorbing hydrogen. Nickel can as well. It's slightly less reactive. So you get this surface where you're getting both of these, and then what this does is we get the possibility of, or we get the addition. So by coordinating that bond, you've weakened that pi bond, and you've broken the hydrogen-hydrogen bonds, so that what you end up with is then, the hydrogens adding there, and because they're coming in this way from the surface, this is a syn addition. And remember that syn addition is the same sides. We're adding both those hydrogens on the same side. What that means is if we look at the stereochemistry of, let's say, a species like this, that we're going to end up with something like this. get syn addition, right? So we'll only have these two isomers. So both the hydrogens, whether they add from the bottom or the top, and again, remember that's because this starts planar, right? That we're going to get these two enantiomers. If we had done something like this, and this is just to remind you of chapter 5, right? If we had done hydrogen, palladium on carbon, and again, I can put platinum, palladium, nickel. I can interchange these catalysts, so that doesn't change the reaction. Right? If I did something like this, both hydrogens both add to the same side. But in this case, right, this is a meso compound. So it doesn't have an enantiomer. So if this had been a symmetric molecule to start with, then we would end up with a meso compound, both hydrogens adding to the same side. Okay, the book also looks at homogeneous catalyst and asymmetric catalysts. We're going to focus on, I'm just going to introduce the homogeneous catalyst. We're not going to spend a large amount of time on the asymmetric homogeneous catalyst. Here we still use hydrogen as our main reaction, but then we can add a different catalyst. Here we've got Wilkinson's catalyst. Wilkinson's catalyst is rhodium, right, with a chlorine. So we got these 3 triphenyl phosphine. So the phenyl is this group, right? So you can see this is a big organic molecule with a rhodium in the middle. This is Wilkinson's catalyst. Okay. The advantage of this one is that it's homogeneous. The result is still, a syn style addition. Now, where the asymmetric, and again, I'm not spending a lot of time on this, is because I can change. Let's say that I change and substitute one of these groups. I can start to create it's ugly, so let's clean it up. I can create a chiral catalyst. Right, so if I start with, some group, add a chiral catalyst, right, I'll only end up with 1 enantiomer. So the way this works is if you have achiral and achiral, you can't create chiral. But here, if you have chiral and achiral, you're starting with achiral, and you have chiral, then you can create chiral, right? So the asymmetric, the idea behind this is by going from a heterogeneous to homogeneous catalyst, I can create a homogeneous, a asymmetric, a chiral catalyst, and then that chiral catalyst can create single enantiomers of hydrogenation products. I'm not going to focus on it. It's important to understand the idea of chiral catalyst. That's one of the reasons the book has it here. But I'm not going to focus a lot on it. You should be familiar with Wilkinson catalyst, and you probably will see something related to that in the mix. Okay. All right, so that's hydrogenation. Hydrogenation, there's not really a mechanism on that one. The mechanism is the absorption of both the alkene and the hydrogen to the metal surface. Okay, so now let's look at hydrogenation. Oh, halogenation. Generically, it's going to be taking a halogen and adding it across. We have slightly different mechanisms depending on what we have. I'm going to focus on bromine. So in the first one, we have the alkene reacting with bromine. What's happening, what's going to happen here is, if you remember our mercury, well, a couple of things that we need to talk about here. One is that we get a partial positive and a partial negative, right? Why would we have two bromines where one is partially positive and one is partially negative? Well, this is an instantaneous dipole. Right, remember van der Waals or London dispersion forces? This is what creates those, right? Is that you get electrons not always well distributed. And in this case, we got two bromines that are attached to each other, and both of those bromines really want that electron density. And so you can see that because they both want the electron density, it's kind of like two toddlers or two small kids fighting over a candy bar, right? It's always going back and forth, and at any one point, the candy bar is in one person's hands or the other. And the smart thing to do is to, get out a ruler and carefully cut the candy bar right down the middle and give it to the children. But in this case, right, you just have this instantaneous dipole. That instantaneous dipole creates an electrophile. So that reacts with the bromine, and then that leaves, but the bromine also has a lone pair, right? So like with our mercury, what we end up with is this brominium ion. So we got our bromine, and I'm going to go ahead and show it going up, right, with the positive on it. Because the bromine forms this brominium ion, we end up with this. That means that then the bromine coming in will ring open this, only attacking from the backside to give me anti-paraplanar. Okay, so this is an anti-addition. The anti-addition always occurs with bromine. Most books show it with chlorine. It happens quite often with chlorine, and it happens most of the time with iodine. But with bromine, it's always going to form the brominium ion. Okay, so if you'll notice, the book tends to show bromine a lot, and that's the reason why. It also turns out bromine is slightly easier to work with than chlorine gas. Bromine gas can do it too, but chlorine gas was the first nerve gas used in World War I. They literally took canisters of chlorine and just opened the valves on the trenches and let the gas blow across. So quite devastating. But here, bromine, we get the anti-addition on our bromination. Okay. Questions about this? So you'll tend to see bromine as the main reagent, although the chlorine and iodine also work. Okay. Thing we need to look at is halohydrin. If we take a halide, but now do the reaction in water, we'll end up with a halohydrin. The mechanism is very similar. I don't know. My hand's sliding today. So again, we start with that bromine. All right, one of the bromines is going to be electrophilic, the other one will be partially nucleophilic. We get loss, electrons come back, react to give us our brominium ion. Okay, now at this point, okay, water is part of our solvent. And the question you have to ask yourselves is which of these is in the higher concentration, right? The bromine ion that I just created or water? Well, how much bromine will I have, bromide ion will I have at any one time? Well, the only bromine negative I'll have is going to be what I created, right? So the concentration of bromide negative is always going to be low. So therefore, the correct answer is a solvent. Water is going to be in high concentration. Water is a good nucleophile, right? So this is going to ring open this brominium ion, and I forgot to put my positive, so don't forget to correct that. And that gives me then the bromine. Again, it's anti-addition, right? I get this, and of course, I need a proton transfer. So another water molecule is the most likely base to do the proton transfer to get me to the final product. Okay, so we have nucleophilic attack the bromine, leaving group leaves, lone pair comes back to form the brominium ion. Then the brominium ion is attacked by the solvent, right, which is my water. That creates this protonated species, proton transfer to give me my halohydrin. Okay. So therefore, what you're going to see is if we wanted to have this addition without the halohydrin, right, I'm going to add something like methylene chloride. And often what I'm looking for is something that's referred to as a dry solvent or can be easily dry. So methylene chloride, it's easy to keep methylene chloride dry, meaning there's no water in it. It's not dry as in the all and it's a solid, it's dry because there's not water in it. Other ones are ether, chloroform, which would be CHCl3. Methylene chloride is the common one that we use at this level, but what you want here is a non-aqueous solvent, and a solvent that's easy to dry or easy to remove all water. Okay. So when you see these reagents together, this tells you that I'm getting the halogenation. If we did the same thing but change the solvent, I would get the halohydrin. An extension of this is that if I did it in an alcohol solvent, I wouldn't end up with a halohydrin, but it is possible to end up with the halide and the ether, right? So all I'm doing is changing my reactive solvent. My solvent here is the methanol. I still get the proton fine, and I can get this product. Questions about halohydrin formation? Oh, there should be a question about halohydrin formation, which is regioselectivity. So we've already looked at the stereochemistry, right? The stereochemistry here is anti-addition. Now we need to look at regiochemistry. And what we see is that the water adds to the more substituted side. Okay, the reason for that is that, like with the oxymercuration, demercuration, we end up with our species here, right? And if we think about you know, this three-membered ring being very sterically hindered, are very strained, right? So we have partial positive here, partial positive there. So as this gets strained, if we think about it trying to release some of that strain energy because of this tight three-membered ring, which of these two is going to be more stable? The one where the partial positive is on the tertiary, or the one where the partial positive is on the secondary? Well, the partial positive on the tertiary, right, is more stable. So therefore, whenever that alcohol comes in and attacks this to ring open, what you can think about is that there's going to be more partial positive charge that position is going to be more electrophilic, and so I'm going to have attack at the more substituted side. Right, and then a proton transfer. So the stability of that partial positive at the tertiary position, right, is what drives the regiochemistry here. And I haven't shown the anti-addition, but it would be anti-addition here. Okay, so the regiochemistry is Markovnikov. Well, you're adding two things around it, but the alcohol is Markovnikov. Okay. So I've added the electrophile across, right? There's no full carbocation, but then the OH adds to the more substituted side. Okay, question about halohydrin. what we'll end up on today is dihydroxylation. Okay, so dihydroxylation is taking the double bond and adding 2 hydroxides, right? So we're adding 2 waters to the double bond. Yes, I'm sorry. Things came up yesterday and wasn't able, office hours. I'll try and have some on Monday and Tuesday, and Monday or Tuesday, and then I'll try and have some more on Wednesday and or Thursday. So I'm trying to have at least 2 sets next week. All right, so if we look at this one, so we have 2 possibilities, or 2 things we need to look at. One is anti-dihydroxylation, and the other one will be syn dihydroxylation. For the anti, the first thing we're going to do is create an epoxide. An epoxide is a 3-membered ring with an oxygen. And then we're going to ring open that. With, for this chapter, we're going to ring open that with acid and water to give us the dihydroxylation. So this first reaction is with a peroxy acid. Peroxy acid is a carboxylic acid with 2 oxygens, right? It actually turns out that this bond right here is relatively weak, and it turns out that that oxygen is electrophilic. So therefore we get a reaction with that electrophile, and then we get something called a cascade. So we're getting the oxygen, the electrons going here, this pi bond going up here to pull off that proton, and then these electrons going back to that partial positive forming on that carbon. So that gives us this epoxide, right? So we get both of those adding to the same side, right? So that's why they're both dashed there. And then we get our protonation. So then the epoxide is activated by protonating it. So we get a proton transfer. Once we have the proton transfer, then the water comes into attack. Now, in this case, it's symmetric, but it would attack the more substituted side. And since both of these are alcohols, you usually can't tell the difference, but it would be attacking the more substituted side. That gets this plus the protonated alcohol. And then another proton transfer. To get us to the final product. Okay. So we get this interesting peroxy acid process, but notice that this is similar to the oxymercuration demercuration. So the first step with the mercury there, and it is similar to the brominium. Now it's a little bit more complex, more arrows, but it is the alkene attacking electrophile, and then electrons coming back from that electrophile to close and make a 3-membered ring. right? So this process we see in 3 different species, right? We see this in our mercury. We see it in our brominium. And now we see it in the epoxide. So that attack of the nucleophile, the double bond on the electrophile, and the electrophile sending electrons back to make the ring are common in all 3 of these. Okay, for our peroxy acids, you will often see just the RCO3H. That's pretty common. Of the ones that you'll also see is this one, which is the acetate. So it'd just be, you know, shorthand would just be CH3C3H. The other one you'll see, and this one has an abbreviation based on its name, which is meta chloro per benzoic acid. Right, and this is known as MCPBA, right? And you'll actually see that. Sometimes you'll see this, where the M meta is often an italics and small. Okay, so these will be the main ones you see. What you're watching really for is the peroxy acid portion, which is that. Of course, with the MCPBA, it doesn't show it, but in most of the cases, it'll show the CO3. Okay. Questions about anti-dihydroxylation? Okay, we'll finish up today with syn dihydroxylation. Okay. So in this one, we're going to see several sets of reagents. The common part is the 4 oxygens they have. Osmium tetroxide is one. The other one will be potassium permanganate. The main way that these work is that when we add, and both of these are very similar reagents, when we add the osmium tetroxide, we end up creating this species. If we do permanganate, we end up with something very similar. Right, so let me redraw that. That's kind of ugly. So we end up with this species, right? And this is where we get the syn addition, right? So the osmium tetroxide starts out as a planar species, so therefore both of those oxygens have to come from the same side, so we get syn addition. This is the step that determines the overall stereochemistry. Then we get a reduction, so that's what the sodium hydrosulfide is. Right, and what that does is then get us to the final product. Right, so the syn addition is what gets us there. Now there are multiple reagent types. Let me show you those so that you can see what the differences are. So I could have one osmium tetroxide followed by the sodium hydrosulfite in the water. We can also have osmium tetroxide followed by disodium sulfite. Right, notice similar reagent, just 2 sodiums instead of 1 sodium. The other one is using catalyst. So osmium tetride is toxic. So you know, it's not good to use quantitative. So you can have catalytic amounts of osmium tetroxide with MnO, right? And MnO is this molecule, right? What's happening is the MnO is oxidizing the osmium back up, creating the product, but then recreating the osmium tetroxide. So the process is reductive, but the MnO is a mild oxidant. We can also do this with osmium tetroxide and something like the peroxy alcohol, right? So here is the peroxide, right? And then the other one I showed you, which is the KMNO4 in base. So all 5 of these combinations, notice the first 4 have the osmium tetroxide, that's how you recognize it. The other one is the KMNO4, the way you recognize that is as 4 oxygens, right? All of these go through this intermediate here, whether it's osmium or manganese, and then a process to where it becomes the dialcohol. Okay. With that, it looks like we've run out of time. So I will send an email about the quiz once that is up. I'll send an email about office hours next